Okay, so I want to talk about a baby with a brick. Okay, so very realistic scenario, one that I hope to have played out in my family's future. We have a baby playing with a brick, and you can tell that it's a baby because the head is about the same size as the body. Okay? And this baby is pushing on this brick, trying to slide it. Now I want to say something about the floor first of all. The coefficient of kinetic friction on the floor is, or between the floor and the brick, is 0.500. And I'd like to say that the mass of the brick itself is 10.0 kilograms. This is my son, by the way, who will be as strong as his daddy. And you can see that this little boy is pushing a 10 kilogram brick across a frictional floor. Obviously he has guns like mine, right? Like, you know, concealed weapons underneath of these sleeves. So he's a tough one. And he's going to push with a force, because he is so tough, 100 newtons. I know, right? So we're going to say F applied is 100.0 newtons. And the angle at which he's going to push relative to the horizontal is 30.0 degrees below the horizontal. So here's the question. And it's not much of a question. It's not a very long question, but the answer takes a little bit longer than the posing of the question. As usual, we'd like to find the acceleration of the brick. So the first thing we always want to do is draw a free body diagram. Give me some forces. What are some forces acting on this brick? Mass?
If I plot x is sine f of y,
Oh.
sine 30 f of y.
Are you just coming up with that? Yeah. Okay, well, let's talk about the f applied x then. You're right. So I want to go back to the illustration. We could call something f applied x, FAPX if you like, and if you wanted to, it would be f applied cosine of 30. Yeah. So I'm going to say in the horizontal, I've got FAPX, which is FAP times cosine of 30 degrees. And you said f applied y as well, right? So f applied y, FAPI, which always makes me smile, which is f applied times the sine of 30 degrees. And again, that just comes from the triangle that you could come up with. You know, it's a right angle triangle that you could come up with up in the illustration up here. But I never like to draw the triangles on the free body diagrams because we always just want to draw the x and y components of forces acting outward from the center of mass. What's another force that could be produced, or could be placed on this FBD? Yeah? Force due to gravity, I like it. So we've got Fg, which of course is just mass times acceleration due to gravity. What's another one? Yeah? Friction, yeah? So we've got our Fk value, which is equal to mu k times the normal force. And one more. At least one more. Yeah. No, we didn't say normal yet. And I don't want to write down an equation for the normal force just yet. Okay, what I do want to do right now is ask for your help in calculating F applied in the x direction and F applied in the y direction. Can I ask you just to take a moment and calculate the numerical values quickly? Oh, and while you're at it, Fg. Although Fg, I'll admit, is the easiest one. Which one is that? X. Okay. So, can you see that? Where's the marker to find? Okay, so 86.6 newtons. F applied y is 50 right on. Newtons, and Fg is 98.1? 98.1 newtons, because it's just 10 times 9.81 meters per second squared, if we're assuming Ag is 9.81. Now, some people just want to say, all right, so F normal has got to be the sum of these two, but I do want to be as communicative as possible here with finding my F normal. So I'm going to go through that process that I mentioned before, where we say that F net in the y direction is equal to F normal plus Fg plus FAPI. Okay? Because that's probably the most expressive way, because what I've been saying up to this point is that F net should always be written as the sum of the picture, right? F net represents the picture, the sum of all the vectors in the picture. So I don't want to diverge from that. So if I want to get F normal all by itself, I say F normal is equal to F netty minus Fg minus FAPI. And we plug in our values. So if we call up positive and down negative, if we call to the right positive and to the left negative in our reference frame, I should say up, down, right, left. We plug in our values. F net y, well, what is F net y? It is 0, yeah. So provided that this brick isn't falling to the center of the earth, the F net y is 0. So we just say 0 minus Fg, which we said was 98.1. Well, actually negative of negative 98.1, so minus 98.1 newtons minus negative 50.0 newtons. The negative signs take care of the direction for us, and we end up getting positive. Well, what's 98.1 plus 50? Would you believe 148? Okay. Positive 148.1 newtons. And so we've got a value now. 148.1 newtons. And we communicated it fairly properly too. And like I said before, if instead of writing 98.1 there directly, you feel more comfortable with actually writing in mass times acceleration due to gravity and writing this as a massive equation with all the variables showing, that's beautiful. You should do that. You'll have less rounding error. I'm just trying to show this for clarity's sake, okay? All right, so we have F normal as 148.1. What's the next step? What should I do next? Yeah? Find the friction, right? We've got normal now, so we can actually calculate the friction. So I'm going to do that over here. Fk is equal to mu k F normal. And again, if I wanted to, I could write this in general terms. I could sub in this whole expression in brackets into the F normal spot. But I think that maybe it mystifies things a little bit at this level. So we're not going to do it, but you could. You absolutely could. And it might be considered to be more correct to make this enormous equation with mu k out front as a coefficient. So plugging in our values, 0.500 times 148.1 newtons. Oh, you're so fast. Even beat Ferlin this time. He doesn't have his calculator and he almost won. Huh, wow. All right, 74.05 newtons for the FK. Now what do I do? What next? Yeah.
Would you be able to subtract that from F of y x?
Yeah, I like that. Actually, I would write it a little bit differently though, but I like the way you think about that sort of thing. What I would say is F net in the x direction, F next for the dyslexics. F net in the x direction is equal to F applied in the x direction plus Fk. And I can get I can figure out what F net x is by plugging in those values. F applied x was, what was it, 86.6 newtons? Okay, taking it from the free body diagram. And Fk we just figured out as negative, and I'm having a dialogue with the conversation, or I'm having a conversation with the diagram here rather. 74.05 is pointing to the left, which we previously said was negative. So I have to make sure that I keep track of that. So it's minus 74.05 newtons.
So does that mean that the mu k has to be negative?
Mu k isn't negative. It's actually has to do with this formula here. Fk is actually mu k times the normal force, the absolute magnitude of the normal force, with the condition that Fk is always going to be pointed in the opposite direction to the net force otherwise. So it's just something that you unfortunately just need to remember. Okay? All right, so 86.6 newtons minus 74.05 newtons. What do you get? 12.55 newtons. Now what do we do? Do you remember what we were trying to do in the first place? We were trying to find the acceleration of the system, or of the brick, sorry. Yeah, just F equals ma. You know what? I'm not even going to write F equals ma. I'm going to write A equals F over m. Or 12.55 newtons over, we said the mass was 10 kilograms.
Yeah.
I've just run out of space here on my paper, so forgive me for my horizontal equal signs here, but I'm just going to have some bad form. 12.55 divided by 10, you get 1.25 meters per second squared. 1.255 meters per second squared, or approximately, I think we had 3 sig figs to start with, so we could say 1.26 meters per second squared. And we're done. Now, it seems like a lot of work, and if I presented it to a grade 11 group, they might find it a bit intimidating, but hopefully, is everybody able to follow that? It reads like a story, right? Like a beautiful, beautiful fairy tale.